Hello, my friends. This is Deepak again, and we are very fortunate today to have two amazing scientists join this conversation. I picked up their book at the airport the other day, and I haven't put it down since then. In fact, I've read it many times. Where did the universe come from, and other cosmic questions. And the two authors are Dr. Ferrie and Dr. Lewis. Dr. Ferrie is a quantum physicist and is associate professor of quantum software and information at the University of Technology, Sydney. And Dr. Lewis is an award-winning astrophysicist and professor of astrophysics at the Sydney Institute for Astronomy. We'll be sharing all the links with you, and this is the book that I've been reading and gifting to people. As you know, on these conversations, we've interviewed some very interesting people, including Caltech professor Sean Carroll. We've interviewed MIT professor that got a Nobel Prize. His name skips me right now, but on and on. And I have to say, this is the most succinct discussion I have read on the conundrums, both in quantum physics and general relativity. So I'll start by asking Dr. Ferrie the first question. And that is, as you know, Dr. Ferrie, quantum mechanics is a perfect recipe for creating all the technologies that we have these days, including the conversation we have right now. But if I go to Wikipedia, then I read like 30 different interpretations. And if I'm not mistaken, until recently, the Copenhagen interpretation seemed the most popular, but it's been taken over by multiverse and now all these other theories, time symmetric theory and teleological theories. What do you favor, sir, as your particular take on the meaning of quantum physics?
Sure. Well, that's a great question. I think the Copenhagen interpretation is certainly still the most popular amongst practicing scientists. So the ones that are building the technology, which outnumber to a vast degree the ones that are trying to communicate the science. So it's kind of a boring interpretation, so it's not that popular amongst people who want to communicate it to the public, but most physicists subscribe to that Copenhagen interpretation. I happen to like, some version of that, Niels Bohr's sort of private interpretation. Sometimes it's called the Bayesian interpretation.
I saw that.
Yeah, so I'm a agent in the world. I have my experience, and that's all I have. That's all I can really be certain of. And I use quantum physics as a tool to help me navigate the world around me.
Yeah, and the tool works, but obviously the meaning is still kind of elusive. One of the problems I've had as I go to all these conferences on quantum physics and, everything that you're discussing, because I'm just mystified by the fact that we exist. And it's a bizarre thing that there is something called existence. And then we have Homo sapiens trying to figure it out. And I'll have questions to ask your colleague in a moment about who's trying to figure out what, but I do go to these conferences where everyone talks about the observer, but where is the observer? What is the observer? Current science cannot find an embodied observer. In fact, even the body is an observation. So without knowing who or what the observer is, kind of becomes very difficult to actually talk about these matters.
Yeah, I definitely agree with that. I use science. We can use science where it works best, right? So I see science as a collection of stories written in the language of mathematics. And these stories are about things that we observe in the world, patterns that we observe and we'd like to explain and perhaps even control. And to do that, we caricature that thing that we want to observe and control and explain. And in doing so, we leave out everything else, right? We have these like models of gravity. There's a ball, or anything that's falling. It's a sphere. It has a center of mass, and we ignore everything else around it. And that's our model of this phenomenon, gravity. And we can look at all different other sorts of phenomena, but there's no reason that these things need to be connected. And the sort of the ultimate phenomenon of reality has to be caricatured in a way that really removes, removes that inner self, right? That thing, my experience can't be explained uh, within that external theory, right? Because I have to be able to share that theory with all the other scientists in the world. So it, I think that's really the crux of the issue, is that science at the outset just says that our personal experience is not something that we're going to be able to explain.
The hard problem of consciousness.
That's right. Yeah.
Yeah. So as I read your book, it's very obvious to me that you're interested more than just the recipe of quantum mechanics as a math principle. But I do have a question. We have this famous statement, I forget by which physicist, the unreasonable effectiveness of mathematics. So why is mathematics so effective? And where is this thing, this activity that we call mathematics? Why is it so unreasonably effective? And is it some activity just in human consciousness? Or is it a fundamental activity in the universe itself? And not to mention, and I'll let you go after this because I want to talk to your partner as well and come back to you. What about Gödel's theorem? And, there's so many conundrums even in the mathematical model. But what's your take on mathematics? Theoretical physicists are mathematicians. They could like to kind of distinguish themselves from experimental physicists. I presume you're both.
I work closely with experimental physics. So, I step in the lab and do experiments, or at least sometimes they let me poke things in the lab. On the topic of mathematics, I would disagree. So it was Eugene Wigner who wrote.
Right.
Yeah. So his birthday is coming up, actually, 17th of November. So he wrote this article, this sort of famous popular article, The Unreasonable Effectiveness of Mathematics. And I think I would disagree with him, actually. It's quite reasonable when you think that mathematics is a tool invented by humans to create these stories. And, by intention, we're going to keep the stories that are most useful to us. Right. So that's why they seem so useful. That's why mathematics seems so useful, because we created it to be useful at the outset, and then all of these other theorems they start to make sense, like Gödel's theorem about the incompleteness and things like in computer science about uncomputability and related things. They all start to make sense. At, at the core, deep in my heart, I'm an applied mathematician. I I use this tool of mathematics to solve real world problems. And I sometimes you take a few steps ahead and you look and yeah, it's really complicated. Like there's a lot of stuff we don't understand. But then, I step back and say, okay, what can we do? Right? Let's start from what can we do and start pushing forward. And we can make speculations, but let's not get too far ahead of ourselves, because it's just so far away. And I think perhaps that'll be the view of most applied mathematicians or engineers. And I think the kind of relationship between somebody's thoughts and mathematics are different, I think, for theoretical physicists. So maybe Geraint has a different point of view on that.
Yeah, may I add to the answer?
Yeah, please.
Dr.
Lewis.
Because I think there's actually an anthropic argument hidden here as well. I think the fact that we can describe our universe in terms of mathematics means at some level we're in a relatively simple universe in which we can have science, we can make predictions, and it's in that relative simplicity that has allowed us to exist. If we had a universe that wasn't governed by regular mathematical principles, there would be no such thing as science. There would be no way that things would do the same thing twice. And so we wouldn't be here to answer the question. So this slides into the multiverse kind of area. But in my opinion, it's related to the simplicity of the universe more than anything else that mathematics is effective.
That's very interesting, because my next question was going to be that since right now mathematics is giving us a lot of very interesting insights in both quantum mechanics and in your field, general relativity, I want to ask you whether you feel that the mathematics as we know it now actually will one day validate what we call the standard model. As you know, there are problems with the cosmological constant. There are many other issues that haven't been addressed. But I would like to ask you, do we know if there's a cause for the Big Bang? Number one, do we know why cosmic inflation was so precise? Do we know if there were any such thing as laws of physics in the so-called Planck epoch? And if the measured value of the cosmological constant and the theoretical value don't match, and they're so far off, and yet these recipes seem to work, that's, a source of confusion for all of us who are novices, who don't really get your field as well. And for Dr. Ferrie, now that we have this whole thing of quantum entanglement in math, is that going to lead soon to quantum computers? Since you seem to be a specialist in quantum software, and how is that going to change everything and that we experience today in the world of technology? But first, perhaps, Dr. Lewis, you could address those questions I asked.
Oh, yes. I mean, there's a very simple answer here. And in truth, we don't know the answer to many of those questions. When we look at modern science, cosmology, quantum mechanics, we all agree that they're incredibly successful theories when they work. But we definitely are left with questions that are not yet answered. Where did the universe come from? The title of the book is, in reality, we do not know, and but we know why we don't know. And that's because quantum mechanics and relativity are written in two different mathematical languages, and making them work together such that we can see through the earlier stages of the universe and answer the question, where did the universe come from, is something that we haven't achieved yet. Similarly, questions like the size of the cosmological constant, the apparent fine-tunedness of inflation, they are unresolved, and we don't know if they are going to give us a solution within the maths that we have to describe our universe, or if there's a bigger picture that we need to find that solution. So a question like the fine-tuning of inflation, that might be related to the process of creating universes. This is this idea that, of course, we are just one universe within the multiverse, and the conditions that we have were somehow chosen, I'll put in air quotes, that there's a universe generating mechanism, and our universe got imprinted with a particular set of laws of physics, and that set inflation, the cosmological constant, etc. But until we can build our mathematics up to a stage where we can describe the multiverse and stuff in the multiverse, if that is a mathematical theory that works, it's an unknown.
Dr. Lewis, the scientific revolution is only 500 years, and then the major sciences, relativity, both special and grand relativity and quantum mechanics, are only 100 years. And it's very interesting to me that here we are on a little planet somewhere in the junkyard of infinity. And, I'm told, I want you to validate whether this is true or not, that cosmologists now believe that there are 2 trillion galaxies, that there might be 700 sextillion stars and uncountable trillions of planets, possibly some habitable planets, even in our own Milky Way galaxy. Given that, our planet is not even a speck of sand in all the beaches that of the world. And on this particular planet, we have a species called Homo sapiens that's been around for maybe 200,000 years. The scientific revolution, as I said, 500, 100 years. So it's kind of astonishing and mind-boggling to me that here is this one species that has 98.7% of the same DNA as a primate. And now we're kind of exploring the far reaches of the cosmos. And that, I recently interviewed Avi Loeb. I don't know if you know him. He's astrophysics at Harvard. He claims to have discovered this object that he thinks is a technology object out from another solar system. All this is very confusing to me. I just want you to know if you actually agree that there are 2 trillion galaxies possibly, and all the information I just shared with you.
Oh, yes, look, the number of galaxies within the observable universe, that is something we've more or less counted, right? I've actually been to a telescope and taken a deep image, and the closer you stare, the more and more galaxies you see. So they're almost uncountable. There's just so many of them. The question you have about the human mind, I am astounded that, this brain, which, for most of its evolution, was worrying about being eaten by a lion and trying to get the next meal off the hyenas or whatever, that we have been able to do so much in such a short period of time. But it also makes me worry that we might not have the brain capacity, ability to answer the questions that we want to answer, right? We think that we are smart and we could think about anything, but we clearly have physical limitations. There's only so many neurons you can pack inside a head. And we might not even have the imaginative ability to come up with the mathematics, the picture, or whatever we need to really answer the question about where things like the universe came from. So yeah, I don't know. I don't understand why I am able to think about these things. I'm glad that I can, but it is rather terrifying at times.
Dr. Ferrie, on quantum entanglement and future of quantum computers, would you have a comment? But also one more question. If there's quantum entanglement across space, that implies that there's quantum entanglement across time, or does it not? That, that this entanglement exists across the entire fabric of space and time, and therefore past, present, and future are also entangled.
Yeah, I think at least from the point of view of gravity, there's a force that exists between every 2 things in the universe. But it becomes so weak that there's a force of gravity between me and some other galaxy, right? But it's just so imperceptibly small that there's no actionable thing I can do with that information. And the same thing would be true of more abstract things like entanglement. It's interesting. Yeah, I think our brains are hardwired to understand the scales that we inhabit on Earth, right? We going really fast, being near things that are really, really heavy, and trying to imagine being in a place where quantum mechanical effects are relevant to my perceptions, we're just not built to understand that, and probably physically we're not built to survive that. But yeah, I mean, so it's interesting to speculate, but there would never be a time that we can imagine where we would have, say, observational data to go off of, or our own immediate perceptions to go off of, to really know what that would be like. So on the topic of quantum computing, that's something we can do here and now, right? That's technology, and we can do that on Earth in the conditions that exist on Earth without having to worry about potential connections to other things in the universe. Well, I will say that cosmic rays coming in and destroying your calculations are something that's real, but we like to ignore those things. I think when you sit on an exponential curve, when you look back, everything looks slow, and everything ahead just looks like impossible. And so, we will have quantum computers, and when we do, we'll look back and we'll say that that wasn't that interesting, right? That's history. But when we're there, it's going to be revolutionary in ways that we just can't imagine right now.
What do you think are the implications of quantum computing for civilization and technology?
I hope that quantum computers can solve the problems that we think it can solve now. So being able to simulate chemistry on the quantum level will allow us to design new materials, new drugs, new fertilizers, say, and these would have a huge impact on society, potentially positive impact. There's dangers with all technology, so we haven't really carved out exactly what those dangers would be with quantum computing. I again, it's hard to imagine. You have to remember when we built the first transistor, the first application of it, I think, was in hearing aids, right? Nobody imagined that we could do this, that what we're doing right now. That would be complete science fiction. So what we'll eventually do with quantum computers, I don't know, but I know that the path to get to that point will be slow, in the sense that everything has to be compatible with what came before. So if you had a quantum computer today, you would use it in the same way that you use a computer, because otherwise it wouldn't be useful and people wouldn't buy it, right? So a car today has technology beyond the wildest dreams of Henry Ford, but he could sit in the car and drive it off right away because the interface is the same. So to us, it's not going to feel different, right? We can see today that we can manage and cope to a large extent to huge transformative changes in the world. During the pandemic, we're just having a conversation like we would have before, but massive changes have happened. But it's slow enough that we, things change slowly enough that we get used to it. And the same will be true of quantum computers. It'll be slow, and when we stand here and look ahead in time, we'll just be baffled that it will be science fiction. We wouldn't believe it if that it could be true. But when we're there and look back, we'll say, yeah, that was obvious.
I've been speaking to two extraordinary scientists, and this is the book, guys. You need to read it. Where did the universe come from? And other cosmic questions. I just want to give you a heads up on some of the content there. Part 1, the quantum of cosmos past. Where did the universe come from? Why is the universe so smooth? Why is there matter in the universe? Where did the elements come from? Part 2, the quantum of cosmos present. How did we unravel the chemistry of the heavens? Where did the chemicals inside us come from? Why do dying stars rip themselves apart? Is the entire universe a quantum thing? Part 3, the quantum of cosmos future. Why don't all dead stars become black holes? Will matter last forever? Do black holes last forever? Is the end of the universe really the end? And part 4, the future of a quantum cosmos. Where have we been? What does a theory of everything look like? Where can a theory of everything take us? What stands in our way? So if these questions puzzle you, you need to read this book. I've been hanging out with all kinds of scientists, and I've never read a succinct volume in such a short, compact book. It's totally complete. So I recommend this book very highly. And please pick it up. I picked it up at the airport, and I've been not only rereading it, but sharing it with all my friends, including those who are philosophers of science. So I'd like to end with one little comment, and I'd like your take, both of your takes on it. So in 1930, there was a very interesting meeting between the Indian poet Tagore, who had won a Nobel Prize for literature, and Einstein. 1930. Of course, Einstein was a luminary at that time more than anyone else, and Tagore was a little senior. And Tagore was traveling in Europe, and both Bertrand Russell and Einstein invited him separately to meet him. Bertrand Russell was very dismayed by his meeting with Tagore. He said the same bullshit Indian philosophy or something like that. And Einstein had a very good conversation, which was reported, I think, in the New York Times, but carried by other publications. I have it with me. And it was a very interesting conversation, because what Tagore pointed to Einstein was the whole problem with what we call realism, is the physical universe that we observe, including our own physical body, real? Or is it actually a human perception, a species-specific interpretation of human perception? And, we know that our perceptions are magical lies. After all, my perception tells me the earth is flat. Nobody believes that anymore. My perception tells me that the ground I'm sitting on is stationary. I know it's spinning at dizzying speeds and hurtling through space at thousands of miles an hour. My perception tells me that you look like what you look, and so does everything else. And yet, that is not really true. You and I are proportionately as void as intergalactic space. And if we could see ourselves and the world as it is, we'd probably see a huge emptiness with a few scattered dots and spots and some random electrical discharges. And even those random electrical discharges or quantum fluctuations are impermanent appearances as determined by what you would call the uncertainty principle. So we are here, we exist. But is it all a dream? Is it all a mirage?
I'll comment first, because I think Geraint, he's so eloquent and says beautiful things. So maybe we'll let him finish with something beautiful. Because my answer is again from this sort of applied mathematician engineering perspective, that all I know for certain is that I have an experience, and everything else is my inference based on my perceptions. As you said, it's all an illusion, right? The screen that I can see you, and I can imagine what you look like in person, but all I'm seeing are photons, or in my model of the world are these little photons that are coming through the screen in front of me, which is made of atoms, which are mostly empty space, right? But again, these are all models and pictures of the world that our bodies and brains use because it's useful to navigate that world. And so reality, I think, is the most we can say and do about it as good engineers is treat it as a model, a working assumption that maybe it's wrong, but it works for now, and it'll eventually be supplanted by a new model that's better and will tell us new deep things that we ought to think are true. But again, that will just be a working hypothesis, and ultimately all we have is our experience and our perceptions, and that's the only thing we can be certain of.
So in other words, for the moment at least, shut up and calculate.
I mean, if you want to get things done, yeah, you have to do that.
Yeah.
But it's good to think about these other things. Like I said, you step far ahead and try to look back and say, how am I going to get to here from there? But the most progress we can make is building on the foundation and building up. But yeah, sometimes you need a bird's eye view.
You've done an amazingly elegant job in this book. I can't congratulate you enough. I'm a big fan already. For our conclusion, Dr. Lewis, last words from you.
Yeah, I've been a physicist for quite a while now, and of course we learn about atoms and electrons and photons, etc. And it can be hard to remember that you actually are talking about the stuff that you're made of. And it's one of those things that you can lie there at night saying, I know I'm atoms, I know that things are all talking to each other. So who am I? Where am I in all of this picture? And I take my comfort from a quote from the Astronomer Royal Martin Rees. He made this a number of years ago, is that a bee is more complicated than a star, right? So to me is related to complexity. The fact that there is so many different connections and things talking to each other, that is the me in the universe. So, and physicists get very scared of complex systems, right? There are people who investigate them, but as you get the numbers of interactions going up, then you get these emergent phenomena, which we are only now really starting to get to grips with. And of course, there are people who think that's tied to consciousness, and that's what we are. So I still think, in terms of understanding the fundamental universe, I think physicists have got the basic picture right, but we've just got the Lego blocks. What we need to do to understand us and reality and how it all fits together is really work out how we can put these Lego together to get the complexity, which is ultimately me.
Well, thank you both. This has been a very illuminating conversation. As usual, I learned more than I could anticipate, and I hope everyone will pick up the book and learn for themselves as well. I'm very grateful to both of you for the time you have given me. Thank you, sirs.
Thank you.
Thank you very much.